We're going to go ahead and look at inverses of functions and inverses of relations today. So let's go ahead and make a t-chart for our y is equal to an 2 raised to the x. So I just chose some values for x near 0. So 3, plug it in, so you get 2 cubed, which is 8. Put in 2, you get 2 squared, which is 4. Plug in 1, you get 2 to the first. Plug in 0, 2 to the 0, which you should remember is 1. Negative exponents again, we covered exponents before. So you should remember that a negative exponent tells you to do the reciprocal. So you get 2 to the negative 1, which is 1/2. 2 to the negative 2, which would be a 1 over 2 squared, which is 1/4, and so on. Then just go ahead and plot these points. 3 to the right, 8 up. 2 to the right, 4 up. 1 to the right, 2 up. 0 to the right, 1 up. 1 to the left, a half up, and so on. Well, when you plot all those points and then also go ahead and connect your points, you would get a smooth curve that looks about like this. This happens to be an exponential function we're dealing with here. We refer to it as an exponential function because your variable's in the exponent. Now, what is the domain of this exponential function? Well, you'll notice your domain, once again, is the types of numbers you can put in for x, or how far left and right does your graph go? Well, it goes to the left forever, and it would eventually go to the right forever if you went up far enough. So your domain ends up being all real numbers. But if you look at the types of numbers you get out, this goes off to the left and gets close to the x-axis, but never touches it and never goes below. So in other words, it's always above, always positive. So we're going to say it's positive real numbers, meaning since we're dealing with y, the output, we're going to say y is greater than 0. Well, let's now consider the inverse. Well, the inverse would have to undo what this function did. So here we put in -3 and we got out 1/8. So the question over here for your inverse is it would have to undo that. What would you have to put in to get out a -3 since that's what you started out with? Well, it's that 1/8. Here you started out with -2 and you got out 1/4. Now you got to undo that. You want to get out -2, so what do you have to put in? Well, that's that 1/4. Now, it's really just taking your t-chart here and flipping your x's and y's around. Plotting your points, 1/8 of a unit to the right, 3 units down. 1/4 of a unit to the right, 2 units down. Half a unit to the right, 1 unit down. Plotting those points and continuing on, you would end up getting a curve that looks like this. Now, your domain is the types of numbers that you can put in here. Your domain, looking at your graph, is how far left and right you go. Well, it goes to the right forever, but it only goes over to your y-axis. It gets extremely close to your y-axis, but never touches it. So you can never have your x value being 0, and your x's are never 0 or negative, which would be over here. Your x's are always greater than or equal to 0 for your domain, and that's what we're saying down here. Your range is how far up and down this red graph goes. It goes down forever here. There should be really an arrow here on the left indicating that it's going down forever. And there's an arrow over here going to the right, and it would eventually go out and go up forever. Since it goes up forever, goes down forever without any breaks, your range would be all real numbers. So, how do we find the inverse of a function if you're looking at a table of values? You switch your x and your y values. Therefore, the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. And that's what we notice back here. Here, our domain of our original was all real numbers, and that ended up going to the range of your inverse. Your range of your original was positive numbers, goes to the domain of your inverse, positive numbers. Now, how do you know, just looking at the graph, how to go from original graph to its inverse? Well, taking a look back here, If we would just take the blue right here and reflect it over this green line, meaning just fold it over that green line, we would get the red. That green line is your y equals x line. If you reflect your original function over your y equals x line, you get your inverse. And so that's what we are saying on this one here. You reflect over your y equals x line. Well, how do we find an inverse function if you are looking at an equation? We didn't talk about that in the previous slide, but to find your inverse when you're dealing with the x's and y's in equation, you switch your x and y in your original problem, and then you solve the new problem for y. Now, inverse function of f of x you would write as, oops, just a second here. Sorry about that. My exponents were removed. Is f with a little -1 as an exponent, or f with a little -1 exponent, and then the of x. Now, your inverse is not always a function. If when you do your reflection over your y equals x line, and it does not end up being a function, your inverse does not exist. So you need to make sure that when you do your reflection, that it ends up being a function. If it ends up being a function when you do your reflection, you actually have an inverse. If you don't, the original problem does not have an inverse. Well, here we have a set of ordered pairs. That's kind of like looking at it as a table of values. We said find an inverse with the table of values, you switch x and y. So to find your inverse here, we've got to flip these two x's and y's. Here, to find your inverse of this one, you got to flip x and y. To find your inverse of this one, flip x and y. Find your inverse of the last one, flip x and y. So if it's just a table of values or ordered pairs, you switch your x's and y's. Here, we're dealing with an equation, which really means this. F of x and y are the same. So once again, to find your inverse, you flip your x's and y's. Then the second step is you need to solve it for y. So you need to get rid of your plus 2. Then you need to get y by itself, so you got to get rid of the dividing or multiplying by -2 by multiplying both sides by -1/2. -1/2 times this, and -1/2 times 2 is your positive 1, and on the right we get this. This is your inverse, so you could write it as f of x equals this here. So to find your inverse of this, you reflect or switch x and y. Your g of x is like your y, so you flip x and y, then solve it for y. Subtract 6. Then you got to get rid of your 1/3, so multiply both sides by 3. Your x by 3, and your 6 by 3. So what we have here is a typo. This should really be a -18, and this should be a -18. So it's really plus a -18. So for this particular problem, you're asked to determine if these are inverses. They'll be inverses if you take your 1 and plug it into the other and it reduces down to x. If it does not reduce down to x, they're not inverses. So in this case, I'm going to take this one right here and plug it in over here for x. So I have my 3/4 here times my input, which is my other function, minus my 6. Distributing through, 3/4 times 4/3 is my just x. 3/4 of 8 is plus 6. Still have the -6 here from the right. 6 minus 6 reduces down to x. Since it reduces down to x, we do have inverses. If it would not reduce down to x, we would say they are not inverses. So we're going to do the same thing here. We're going to check to see if this is an inverse. So you got to take one function, plug it into the other. You have 3 times your input plus 1. So I'm going to take this and plug it in for my input. Now, this divided by 3 times 3, the 3's drop out. Now the 1's drop out. Since it reduces down to x, they are inverses. Let's check to see if these are inverses. So I'm going to take this right here and plug it in for x. So I'd have 2 times my input plus my 1. Distribute through, combine my like terms. Since it does not reduce down to x, they are not inverses of each other. They are only inverses if you take one and plug it into the other and it reduces down to x. And we got the same problem again, so sorry about that.